Good morning. This is a talk on stratified data integration. I'm very pleased to be here, even if in remote. As you can see, my name is Fausto Giunchiglia, and I do hope you like this talk. This talk, I think, covers an issue which is at the core of this workshop, and it describes a general approach that we have developed in my group in like 15 years of work, and methodology which actually we developed thanks to the collaborations with ISI and the RTC. And in many places, some of you, we may find ideas which come from library science in its attempt to really organize a large body of knowledge as it appears in the web. The first notion is a notion of representation. You see, there is a word, and no matter what, when we perceive the word, we represent in our minds. And sometimes then, not only represent in our minds, or even computer represent the word in their memory, but then not only that, but then later on we also express what you've said, what you thought towards others, so that others can understand what you're saying. There are many ways of doing this. In particular, in this seminar, we're going to concentrate on representation based on words. And the key idea is that we organize the representation in 4 components: concepts, language, knowledge, and data. I'm sorry if the photo and the video cover some words. And why so? We see that these maybe obvious organization representation in different components is actually key to our approach. So before moving on, let us analyze what we really mean by these 4 ideas over which you organize the representation. So what are concepts? In principle, there is a lot of huge body of knowledge in philosophy or language, philosophy in general, on what concepts are. In general, here we take concept to be something that we use to encode what we perceive and what we reason about, what we understand. And we take them to be alinguistic. We can think of them following Fodor as alinguistic units which are in your brain, but it's just an idea. Just think of them as identifiers. Identifiers which, however, are connected because they mean something. And here we really use the technology words by the Princeton work on WordNet. So there are examples. So for instance, when I perceive a vehicle, because I see from far something which moves, then I encode it as an ID, like a 9872421. Or I can perceive a car, or I can perceive my car. You see, all of them have IDs, and all of them are kind of different perceptions and different encoding my memory of what I perceive. So this concept, what is concept? Just a set of IDs connected, because as I said, the car is an hyponym of vehicle, or vehicle is an hyponym of car, means that any car is a vehicle, but not all vehicles are cars. But then we have these concepts that you can think as codified in your brain or in your mind or in the computer. That we need to express them in some language. So we can think of a language as a tool which allows to communicate concepts. And I could take a language for a set of terms. So for instance, the concept 124265151 is the concept which has a name car or name automobile. Why are we doing this distinction? We're doing this distinction because, first of all, there are multiple languages. And in the web now, more and more you need to integrate data from different languages. Not only that, but even you have multiple names for the same concept. No matter, for instance, whether you use the word car or automobile, you still denote the same thing. And no matter what you call it, my car or the BMW or whatever, you really mean your own car. So you see, language is the first level of variability in the way you encode concepts. And then there is knowledge, because now you have your own car and you want to describe that part. So you want to really say, what is the case? What are the properties of your knowledge? Well, in our approach, we model knowledge as a set of entity types or E-types, where an entity type is a set of properties associated with a set of properties. So the entity type car, and what is an entity type car? The entity type car is a set of cars. An entity type semantically is a set of instances. How do I describe an entity type car? I can describe as a set of properties like the body style, the plate, the model date. But then we also have another entity type, which is vehicle. Which vehicle, of course, vehicle is more general than car, and therefore the properties are a subset of the properties of car. So like, why so? Because there are vehicles which are not car. So for instance, the plate applies to cars, it's a property of cars, but it's not a property of ships, which is a type of vehicle. So here, what you're saying that for any entity type, where of course an entity type is described in a language, and it is also as an associated concept that I codify as a number. For any entity type, codify with an ID, which is a concept, plus a word, which allows you to talk about it, we associate a set of properties. And this is the third dimension. Then there is the fourth dimension, data. Data is knowledge about individuals. The same way as knowledge is universal knowledge, knowledge about universals, then data is specific knowledge about individuals. So if for any entity type, there are a set of entities of that entity type. So the entity type car is populated by the various cars. In the same way, the entity type vehicle is populated by instances which are cars, entities which are motorcycles, entities which are ships, and so on and so forth. And what is the step from knowledge to data? The step from knowledge to data, as we all know from database 1, is just filling the properties of each such entity with a value. So for instance, the entity my car has a specific plate, has a specific body style, has a specific model date with a certain date, has 4 wheels. So while a motorcycle could have 2 wheels. So this is data. So this basically is a representation. So basically what we did so far, we structure representation in 4 dimensions. And now we get to the reason why we did this. And we get to this point by stating a foundational problem, the so-called semantic heterogeneity problem, which was actually now 15 years ago, was the reason why people invented the semantic web. And what is semantic heterogeneity? We have semantic heterogeneity representation under essentially there are 2 possibilities. There are differences how you represent the same word phenomenon. So the same object in the real world, like me, you call him Fausto, you call me professore or professor. That's a semantic heterogeneity. The same real world phenomenon, me, or my role, is given to different descriptions in natural language. Or vice versa, there are 2 different real world phenomena which are represented in the same way. So for instance, you can talk about Java, and you can say you may mean Java as a programming language, and someone may mean Java as a type of coffee beans. So you see, there is a mismatch. There are the 2 types of mismatches, not much more. Are these mismatches frequent? Of course. They are enormously frequent. Why? Because these problems come anytime a given representation is generated by 2 different people, or 2 different parties, or 3 even more. Different parties mean what? like one in Italy and one in India, and that means diversity in space, or another one is me now and me 6 years ago. So, for instance, 6 years ago, I would have described the same phenomenon like a class in a different way. Why? Because maybe I was younger, maybe I had less experience, maybe I was more enthusiastic. If you think about it, you keep changing the way you describe things very frequently. Is that a problem? Yes, semantic heterogeneity is a major problem. It's actually the main problem why the semantic web, to a large extent, didn't go as far as people hoped. And it's a major problem because it's a major impediment for large-scale data integration. Is data integration a problem? Yes, it's a major problem because the web of data will never happen, will never scale until we solve the data integration problem, until namely we're able to take any two data sets generated in any two parts of the world, we'll be able to make them and put them together, preserving the intended semantics. And clear the intended semantics of the data are in the mind of people who generated the data. So now the fundamental question is, how do we come with the general mechanism by which we scale the data integration to the web level? Notice that the web is succeeding in being the web of people. Look at the social networks. We integrate people, but the integration of data is far from being a solved problem. In this course, in fact, we are getting propose a solution to this problem of the web of data. So because of this, we introduced the notion of representation diversity. We define representation diversity to mean semantic heterogeneity as organized in the 4 layers. So semantic heterogeneity is the same problem. It's exactly the problem that I defined before. It is a problem that, as I said, appears in the web. The representation of diversity is our vision of this problem, at the same time our solution, because we say that the way to deal with the problem of semantic heterogeneity is to deal it as a problem of diversity of representation. A problem of diversity of representation that, as I said in my previous slides, we can deal at different layers, at the level of concepts, at the level of language, at the level of knowledge, and the level of data. There is an L3 in between that is a missing layer that we don't need in this talk, which is rather important. And what is the key point? The key point is what is the key idea? Everybody knows who has real practice, has done real work in dealing with semantic heterogeneity, that the complexity of the problem of semantic heterogeneity explodes exponentially with the number of differences. The idea that we can split this problem in 4 layers is very good. Why? For 2 main reasons. Number one, because splitting a big problem in 4 smaller problems when the problem grows exponentially results in a much simpler problem. Number two, the different types of diversity not only are very different, but they can also be dealt with very specific tools. So as we will see later, not only have we split the representation diversity problem in 4 dimensions, but for each sub dimension, we have different tools to make life much easier. So to understand in practice what I'm saying, let's consider it this motivating example. So this is a motivating example. So this is a guy who is an Italian, and he has a car. There is the same car that he has. So this car is stored, is memorized as car in the database of the UK transportation office. Why? Because this guy lives in the UK. So he had to register the car, and they asked him for this data. But this guy is also Italian. He bought this car in Italy, and it has an Italian plate. So it's registered also in the official register office in Italy. But this car is also registered in the local garage as a vehicle, because the garage, they don't really care about the type of car. So this is called vehicle, is a generic term for the vehicles they host in the garage, because the garage, they host cars, motorcycles, and jeeps, for instance. So you see, even if we are talking about the same object, the three representations very different, and very clearly this is a very minor, very trivial example. In the standard application that we make, in particular work a lot in health, we work a lot on university data. Usually any such entity has anywhere between 60 and 500 properties. So think the complexity of integrating data with more than 100 or tens of properties, which can be widely different. So these are problems we're talking about. So think of the problem of semantic heterogeneity, which is huge. And any two data sets that they're going to integrate, because of course usually you have more than two data sets, sometimes you need to integrate 3, 4, 5, 6, depending on the need. You can be sure that any two data sets will be wildly different. It's amazing the quantity of diversity you can see in data. So let us see in practice here what is the help of dealing with our approach, which is structuring the diversity in layers. So number one, we said conceptual diversity. Well, you see, first of all, here, the one point here, what are we talking? We're talking about car or vehicle. Depending on the need, the same object has been described using a different term. Vettura, which is the second one, is the Italian term for car. So on those one, between car and vettura, there is a difference in language, but in car and vehicle, they are the same natural language, English, but then you have a difference in the level of detail, the level of abstraction by which you describe. So you see, before moving on, we do need to understand that you're really talking about vettura or car or vehicle, but you're talking the same type of objects, because you don't want to compare like apples and oranges. I mean, if you're talking oranges, if you're talking apples, you know that they are not the same thing, and orange is different from an apple by definition. So if I suppose that now I need really to get the data from the two data sets I described before, and you want to integrate this data, and you really want to know everything about this car, and you want to know that these three different descriptions of the same car, then first of all, if you really want to know that towards understanding whether these three data sets, database describing the same car, you need to know that whether they're talking about the same object. So most likely in this case, since we chose the example in this way, you're going to decide that yes, you're talking about the same object. Why? Or the same object or the same entity type, I'm sorry. Why? Because we know that you will know that car is a translation of vettura, and you will know that car and vehicle. So you say, okay, I don't know, but to me, so far, car and vehicle could be the same object. Of course, if they say this is an orange, this is an apple, you will know that you're talking a different thing. But in this situation, we have a compatibility just because the hierarchy of meanings, what we call the hypernym hierarchy at the conceptual level, allows you this level of compatibility, which is not a synonymity property, but is something which is compatible. Okay, now we've done this, but now the next one is really, okay, you have to deal with possible languages. So actually you do the languages, I was already doing that in the previous slide. And here just to describe the diversity of languages. First of all, you have multiple languages. But notice that in the web, of course, you have Italian, we have Hindi, we have English, but on the web, there are a lot of namespaces. There are a lot of logical languages. So you have to deal with multiple languages. You have to do like domain languages. So you will be able to understand that car and vettura are the same meaning, or like that VIN, which is actually VSO VIN, which is the first column or the third data set is actually a namespace that really codifies again a nameplate. So you see now here, in this case, we have what? We have like a word, targa, in Italian, which translates in nameplate in English. We translate in a word in a given namespace, in an XML namespace. And of course, what is the point? If you think about it, the point is that in practice, the net result is that for the same concept, I have multiple names. Here, you have an example, but also for the same word, you have multiple concepts. Why? Because, for instance, you have Java, and Java is a single word which has two meanings. This is what's called polysemy. So synonymity, which is a standard phenomenon, tells you that there are multiple words, one concept, and polysemy is a phenomenon by which you have one word and multiple concepts. Both polysemy and synonymy are pervasive in the data set we usually handle when you do this kind of work. It's really pervasive beyond imagination. So you see, what is the bottom line here? The bottom line is that we need to find a way to go beyond, understand the diversity in the languages, which we may do for different reasons, so that we can go to the diversity in concepts, which is one before, where once you've gotten rid of the language diversity, you still have to deal with the concept diversity. Namely, as I said before in the previous slide, to understand that a vehicle can also be a car, namely that the car and vehicles are compatible. Now we're number two, which language. Now we can go on. Then we go to knowledge. What is the knowledge diversity? The knowledge diversity is very clear here. You have the same E-type car, but you have different groups of properties. And again, you see like you have a car, in one place you have nameplate and target and VIN, which is present to all of them. But speed, which is velocità in Italian, is really is only in the first two. It's not in the. Is also the speed. I'm sorry, is in the only three of them. But the type of body is only in the second one, and the model date is in the first and the third. So you see, you have all the different properties, and these properties now ask you answer the following question: yes, before we decided car and vehicle and vettura were compatible, but we really mean the same entity type. I mean, comparing the predicates, comparing the properties will make you answer this question. Then you're able to make this decision. Are we talking about the same set of entity types? Are we talking about the same set of objects? And this is what is called the knowledge diversity problem, namely the fact that the same entity type in different data sets is described differently. And then we go to the last one, because the last one is the foundational one. We need in the end to know whether we're talking about the same car. So how are we coming now to the last step? How do we know, or do we decide, though we don't really know, from the data sets, the three data sets are talking about the same object in the real world? Well, we know that the name of the entity type, car, vettura, and vehicle, and speed, and VSO, VIN are compatible. Good. So the language is compatible across multiple languages. We have three languages: Italian, English, and the namespace. We know that the concepts are compatible because car is more specific than vehicle. We know that the properties more or less are compatible. Why? Because there are enough properties that they share. So there are different viewpoints clearly, but they share enough properties. And now what do you need to decide? You need to decide whether this is the same object or no. How do we decide? Well, we look at that. We see we call it nameplate, we call it VIN, we call it target, but it's the same. So this vehicle has the same plate. So most likely, unless it's being a cheat, which I assume is not being the case, then it's the same car. Of course, in this case, nameplate it helps a lot, but in the same ways like the birth date, the location place helps in identifying people. But you can be sure that these so-called identifying attributes, this is what I call them, they're not that easy to find, and the situation really explodes quite rapidly. But the bottom line, as you see, that basically if you think about it, I really obtained the certification diversity, which really motivates my talk, which is actually the title of the talk, which is, if you notice it, when I was describing it, I was dealing with these four problems one at a time. But in practice, if you remember the original example, all of these phenomena are happening together. So number one, we were able to deal with different type of phenomena for different layer. Why so? Because the type of problem in different layers is different. And therefore, is that good? Of course, because this means that in exactly the same way as I was describing it, one by one, when you do the data integration, you can implement that one by one, which is exactly what I'm going to get to soon. That's the first. And the second one is that the crucial role of the conceptual layer, I mean the IDs. We needed really to have these understanding, common understanding in this language of thought as you want to think it. And in fact, in our implementation, the conceptual layer is really a description logic theory. It's very solid. It's a theory. It's a logic. And why so? Because we need to start from somewhere in consolidating what we mean. And the point here is that I did not say that before, but there is always a many-to-many mapping across all the layers. And this is exactly what makes it complicated, because the composition of the different many-to-many layers generates the combinatorial explosion, which is the reason why semantic heterogeneity so far has never been solved. But at the same time, this assumption that we are making, and as far as we know, we are the first who are making this assumption in the data integration and the web technologies, allows us to have a common ground of meaning to where to start from. And then, of course, the issue is how do you know, how do you do it in practice? But, and we have ways of doing this, of course, but this one is actually out of the goal of this talk, which is really trying to give you an impressionistic overall vision of the problem of knowledge diversity as a first step into this workshop. So the point now here is that what do we do next? Okay, having organized diversity in 4 layers, now the next step is really to organize also the representation of data in 4 layers. What is the point here? The point here is that when you get the data in input, which is here you see, on the right, they are all mixed. But what we do some kind of a 4-step reasoning, where in the end we get, you see, the 3 data sets uniquely organized in the single data structure. And this data structure is a knowledge graph. Why the knowledge graph? Because the knowledge graph is the way to have a uniform representation of the types of diversity. So what is now becomes the issue? The issue that we get a set of data, like in this case, 3 data sets, which are semantically very heterogeneous, where we have all the possible ways of being different, as from our examples. And we go through 4 steps of disentangling this representation to the 4 layers by producing, in the end, an integrated knowledge graph where all these 4 layers are independently represented and split, so that everything is clear and well integrated in the right place. So what I'm going to do next, I'm going to just tell you how these steps work. The first is the language layer. As from the beginning, the language layer is really how you do the mapping. And the mapping from where? For the language into the IDs. You see, these are the concepts. And this is the language. So you may have like schema.org, which is like a namespace, and Italian could be English or anything. But the key point is that really the key idea that we only use language to go from the words into the IDs. So as from the previous picture, you may not remember, but the language uses it only as interface to the user, nothing else. So in the end, when we go to the user, again, the knowledge graph has a language inside. But as you see in the next steps, there is no language. In fact, two more things I want to say is that all of this is really multilingual. Simply by having a table like this that we do have 1,000 languages and 130,000 concepts, basically not to which you can add all the major namespaces like schema.org, SCOS, DBpedia, whatever. We are able to translate no matter what is a language, both natural language and namespace in input and the data set in input into these IDs. Once you have the IDs, we can move to the next step. And the next steps are we just take these IDs and we connect them. Notice that in this conceptual graph, where all the links are hypernamed, and we're not here that we do not have any words. We just have IDs. These are linguistic IDs, and one of them here is going to be car, another one is going to be vehicle, and so on. And this is exactly what we have in our UKC, which is exactly this kind of conceptual graph, where we have like around 100,000 of such IDs, codified in around 1,000 languages. This is what we call the language entity graph, meaning by this, or LEG, that is really a graph. Actually, it's a DAG, which is like an extended tree, multi-rooted tree with multiple parents, where we just connect all the meanings, as it is usually the case in natural language. Then, this is step number 2. So in the step number 2, we went from language. Not only after that, we went to the conceptual diversity. So noted that level 2 is handled before level 1. In the end of this, we have not only, at the end of this second step, not only we have eliminated the dependency of languages, but because of these links, we know that, for instance, that a car is a vehicle. So this could be vehicle here, and this could be car. So we know that a car is a more specific notion than vehicle. And by the way, we do this to all the words. We do this to the entity types, we do this to the properties, and then in the end, given the situation, we build what is called the entity type graph. How do we build the entity type graph? What is the entity type graph? We connect all the different meanings. So for instance, this could be like a car, and this could be like a plate, the attribute plate. This is going to be the attribute plate, and this could be the value of the attribute plate. This could be like the model, and this could be the value of the attribute model. So basically, and of course, in all of this, we apply all of this, and by doing this, this is the first step of entity matching, or entity type matching, where in this exercise you have algorithms that will take the 3 data sets. We codify the 3 data sets in these graph structures, and then we'll extract the unifying graph. Of course, we do this by machine learning, and we have an algorithm which was published in the last conference on knowledge representation. I don't want to get into these details now because, as I said, this by itself, this will be an entire talk. But the point here is that once we have eliminated the noise from the multiple languages, once we have eliminated the noise from the fact that you have different terms to say that the same object and same entity type, then we do have an algorithm by which we can merge automatically all the entity types to share the same properties. And this will allow us, this is very important. And of course, this will allow us to generate like the properties for vehicle, as for my example, the properties for car, as for my original example. And of course, the properties of car will be more than the properties of vehicle, because this is a usual standard subsumption property which applies in description logic to any E-types that are more general than others. Of course, we do have a constraint, of course, that since in the language, since in the LEG, we know that the car is more specific, is more specific object, is more specific entity type than vehicle, then of course, also in the when we build the properties, and therefore we build what is called the ETG, it must be the case that the property of the ETG are a subset of the properties of the I'm sorry, let me repeat. It must be the case that the properties in the ETG of the car are a superset of the properties of the vehicle, or vice versa. Namely, we need to maintain the compatibility between the words used and what you describe. So if you say that a car is a specific type of vehicle, if you think about it, we must enforce that a car being a type of vehicle can be described as like a vehicle plus something more. Of course, here again, we are not entitled to do this. Again, here we have some algorithm which allow to enforce us. And once you've done it, what is the next step? The next step is really we go to the next step. What is the next step? We really build the entity graph. What is the entity graph? Is a data level knowledge graph. What is a knowledge graph? A knowledge graph is a graph which describes entities. So you see here we have the plate, here we have a property, and this is the value of the property. So we have algorithms. Here we use a Karma Linker, which is a tool that was developed originally by Craig Knobloch and was at ASI in California, and that we then later extended to allow for multiple languages to be integrated in our mechanism. But the bottom line here is that as a last step, having fixed first the heterogeneity of concepts, then the heterogeneity of languages, then the heterogeneity of the schema, we can actually decide whether this car was the same or no. And these are the last steps of our situation. Okay, so this is the process. This is a part of the methodology ITelos. I introduced ITelos last time I was here. That last time I was physically in Bangalore. I think it was 2 years ago. I think, or last year, I don't remember. 2 years ago. And now, based on that presentation, the general presentation I gave 2 years ago, now it's become a reality. Now we have ITelos. Everything I described you as a general idea before now works. And this is exactly what we do. And I do not want to get into much of the details, but basically we do now have a software in the general methodology that starting from the beginning or to the end allows in the end to generate our knowledge graph here, plus all the documentation of in OWL, which will allow to produce the final knowledge graph. What do you have in input? In input, you have like the different data as I described. We have in input the kind of knowledge graph we want to be, the specification of the want to be, and then first we have a phase of identifying more or less with a good level of approximation the kind of knowledge graph we want to build. Then we build the informal model using the ER entity relationship model. Then we build the ontology, and here we use Protégé, but not only, which I know that Protégé I saw for the program I use. And then we do the final data integration based on the ontology built in Protégé, and here we use this Karma Linker tool, which, as I said before, was built together with ISI in California. And clearly, in any step, we generated different files. So here, for instance, during the model, we generated the extended entity relationship model, out of which we build the ontology. We use usually a reference ontology because like ontology that we get from the web or from a repository to make sure that the schema or the knowledge graph is of high quality, and then so on and so forth. Of course, here, again, we teach ITELOS in a 14-week class, so I have no intention to explain to you how it works. Of course, I have no time, but I think the main message here would be that in ITELOS, we do exploit all the different levels of heterogeneity, as I said before. So for instance, so basically up to here, what we do, we only try to understand better the informal specification of the problem. And here, at the beginning, we deal, you see, with L1 and L2 at the beginning, because as soon as the data set translates into the language, then when you go here, so here we do the schema integration, which is L4, and then so therefore here we put together the schema, which is gonna in the end contain all the different data sets, and this L4 data then becomes here, which becomes L4. We get part to this phase, which takes it in input, and then we do the real data integration. Here we put all the data sets, and then out of this we obtain exactly, we do the data integration, the L5 data integration, as we said, which is the data integration, and then here, which then becomes the knowledge graph, the entity graph, as we call it. We call it entity graph and knowledge graph, more or less interchangeably. So this is the methodology that we use, and I hope that I succeed in giving a general idea of why and how this stratification of the semantic heterogeneity in 4 layers gives us a general principled approach to how to integrate different data. Of course, I did not get the details, but why so? Because I did it, to me, was really kind of an international. Actually, as I said, I teach a course called Knowledge and Data Integration, and we teach it, and it's a 14-week course, and the student in this course take in input a problem they need to solve, and it's a very concrete project. And at the end of the 14 weeks, they need to build a knowledge graph. So what I told you now very fast, they just do as part of the exam, and the exam was all online, and we teach with the flipped classroom methodology. And by the way, for those of you who are interested, if you go to this link, you will find the slides of the material. You find the registration of all the lectures. You find the list of all the problems and knowledge graphs that people have developed. And for those of you who have the time and interest of learning how to do data integration for real in practice, we think that this is a good material with a lot of external documentation. As a matter of fact, I really hope that, oh, by the way, yes, so we have a lot of assistants. By the way, we do, in my group, we have a lot of student Indians, and Mayuk, but let me just mention Mayuk, who actually helped me to develop these slides, who was actually in the DRTC master student last year, 2 years ago. He's now been working with me for 2 years, very successfully. And he's really actually the guy in charge of all the knowledge integration of handling all the ontologies based on all the great work and great learning that he did here at Bangalore at the RTC. But also Yamini, who is a master student of ours. So she graduated in computer science, but she's again from Bangalore. It seems that Bangalore, I do seems to have a special attraction to me. Anyhow, this is the KDI team. If you go, this actually is just a snapshot of the site. If you go there, you see that there is a syllabus, the teachers, the order calendar, the material. By material, I mean slides, but I also mean the registrations. We mean the results of the exam. We mean also question answers that you do during the class, and then how we do it. Why is that? Why I'm saying this? Because we really, this course is really developing. Next year, we will, the same class will be taught in Trento, but also in Dublin, also in China, and also in Mongolia. And there are more people doing this. And maybe if any of you is interested in teaching or learning about this class here in India, we are very open. All the material is online. You can do whatever you want. Plus, if you wanted to interact with us, we'd be very happy to interact. Our long-term goal, which we do hope, we have already an agreement with some of these universities. For instance, next year, our hope is to run joint projects across the globe where we build knowledge graphs of interest to everybody. So, for instance, right now we're talking this year in Dublin, and most likely with them during this 14 weeks course, we will build knowledge graphs for health, which is their main area of interest. In Mongolia, most likely, we will work on integrating knowledge graphs, which describe universities and data of universities, publications. It's very much similar, and then extension what Vivo does, for those of you who are experts, and so on and so forth. So these are the first thing I wanted to tell you. The second thing that I wanted to tell you, I'm going towards conclusion, is really that not only that, but in this effort to going online, we build a repository where we run around 1,000 schemas, including some well-known ones that we've collected. There is one collaborator of mine is working on this. We have lots of schemas, and why is that schemas are useful? These ontologies are useful because all our students will build schemas in ITIL. The idea is that they can use them. For instance, you have schema.org. A lot of people use schema.org to do data integration. Why? Because schema.org is most likely the most widespread data schema in the world. But then we also have DBpedia. Some people use DBpedia. Like then we have the ontology for GTFS, Google GTFS. So every student will do build knowledge graphs for transportation, use GTFS, and then we have space we use the European standard, and so on and so forth. Anyhow, this is really, we call it Live Schema Foundry, because this is exactly the kind of repository of schemas that we use to do the data integration. And we see that it's a foundry where you can use to integrate data. And we have two main reasons, which is actually I should have said at the beginning. We are interested in developing vertical domain applications. We are not interested, for instance, integrating data, for instance, like Wikipedia. No, we are interested in specific domains. Right now, we are focusing on health. We are focusing on the digital universities, research centers, and we are focusing on open data for the territory. And this is what we are focusing for these domains. The Live Schema Foundry produces a lot of technologies, a lot of tools which will make your life easier, not only to do data integration, but also to do machine learning. In fact, why so? Because in many of our applications, first you build the knowledge graph, and then you use the knowledge graph to do some machine learning. So for this, I think I'm going a little longer. I'm just pointing out schemas. Let me just conclude. What is Data Science? Data Science is our initiative out of which the KDI course, the Live Schema website are built, which is our attempt to generate tools, software, data, which can be used worldwide towards an attempt towards making it possible for people around the globe to integrate together, work together, collaborate. And two more things. Number one, if you want to see how live schema works, you can go and look at the demo. Otherwise, you can just go yourself into the website and just navigate yourself. For the KDI course, you have the link. And so if you may want to go there and look at the material, maybe used. And then if you go to data chains, you'll see our long-term goal. And if you think you're interested in collaborating with us, not only, anyway, as I said before, you can use all the material online that we have. It's all open source, it's all open. But maybe you can join us and maybe in joint initiatives like joint classes, joint material development, and so on and so forth. With this one, I conclude my talk. I do hope it made some sense. It was clearly high level, but my goal here was not to provide you with a global solution, as I said, but give you kind of introduction to the kind of work we do and also to our initiatives of international collaboration that we're now pushing. Thanks a lot, and let me just close my presentation. And of course, I'm happy to answer any questions if there are. Thank you.